Hi guys, today we are going to be considering another one of the most commonly asked tech interview question, and the problem topic for today will be linked list intersection. The problem statement says return the node where two singly linked lists intersect. If the link doesn't intersect, return null. The intersection of a linked list of two linked lists occur when these two linked lists meet at a point, that is when they share the same node. And we can say that subsequently, if two linked lists can meet, subsequently they will share the same node. So look at this example now. We have the first linked list. On meeting here, it shares the same node with the second linked list here. So this is the point of intersection, and we are asked to return the node at which they intersect. An intuitive way of solving this problem is to use a hash set, and then using a hash set we are going to transverse through the first linked list, that is the first linked list A. Traversing through it, we are going to be adding each node into the hash set. Add this, and add each and every node in the first linked list into the hash set. Next, we can traverse the second linked list, and in the process of traversing the second linked list, we are going to be checking each node in the hash set. Probably it is shared by the first node. Don't forget that if the hash set contains every node in the first linked list, and then traversing through each node in the second linked list, now we are going to be comparing it if it exists in the hash set. If it exists, definitely that node that existed is the node at the intersection. Imagine now, okay, let's say we have added all these and traversed all these linked lists, the first linked list, and we have traversed each node and we added them to the hash set, and then we try to traverse the second linked list B, and add it to the hash set. We see that when we get to this point, it has been present, it existed in the hash set, and so therefore we are going to return this particular node as the node that is at the intersection. So that's the most intuitive way to solve the problem. This approach solves the problem linearly. It has a linear time complexity, so which involve iterating through the first linked list and then the second linked list. So it's a linear time, but it comes at the expense of space. We have to create an hash set, so and then the space complexity is O n plus m, where n is the number of nodes in the first linked list and m is the number of nodes in the second linked list. But can we approach at a more efficient solution that we work in a constant space, that is, we won't have to create any extra data structure? Considering this above visualization as two linked lists can be a little bit confusing. So let's treat it as two separate linked lists, the first one and the second one now, and then the point of intersection, that is the tail node, the point of intersection is the one that is within this diagram here, over here. So what we're just trying to do is that instead of having this confusing visualization, we break it down so that both of them will exist separately. Look at this, is the first linked list, so and this is what is shared with the second linked list. Similarly, this is the second linked list and this is what is shared with the first linked list. So this way now we can think about the solution more clearly. If you observe well, you will notice that the problem will even be much more simpler if both the first linked list over here and the second linked list over here are of the same length. So that way now we can guarantee that we will reach the intersection node. even at the same time. Let's work on that. So here now, let's say both of them, the first linked list A and the second linked list B, are of the same length. You see that placing a pointer at the beginning of A, the head of A, and placing a pointer at the head of B, and transversing through the linked list one at a time, moving both of them at the same pace and proportion, we are going to reach the intersection, the point at which they intersect at the same time. You understand? That is provided they are of the same length. Now, could we replicate this same scenario whereby they are of the same length for a situation whereby the linked list A and B are of different lengths? One thing we will notice is that even though the linked list A and B may be of different lengths, their combined lists A combined with B will be of the same length as B combined with A. I just want you to take it as a okay, let's say the linked list A has a length of 3 and linked list B has a length of 2. A combined with 3, A combined with B will give us 5. B combined with A will give us same 5. So linked list A, if we take this particular linked list now and we combine it here at this point, we will see that it will give us the same length for A and B and B and A. Now look at what I'm trying to say in this scenario. This is linked list A and this is linked list B. So you see that when we add them and we form A and B, it actually gives us the same length as B and A. This is B and A down in the bottom here, where the B comes first before the A. Even though the B actually have a length of 1, 2, 3, 4, 5. So why the A have a length of 1, 2, 3, 4, 5, 6, but because we are joining 5 and 6 together to form A and B, and still joining 6 and 5 together to form B and A, they both have the same length, just that one is coming first before the other. And one thing again, aside from having the same length, is that their combined list like that of A and B and B and A, we still have the same shared tail node. You understand? If you look at it very well, look, these ones are not shared, but right from this place they are the same shared node, even as these ones for B. You know that B is 5 and the first 2 are not shared, but the last 3 are shared. And the same thing, A is 6. You understand? I mean, A consists of 6 nodes and the first 3 are not shared and the last 3 are shared. So apart from the combined giving us the same length, they will even end with the same set of shared tail node. Now you see that the analogy that we explained the other time of placing a pointer at here and transversing through the each linked list of this combined linked list, traversing it proportionally in the same proportion, we are going to end at this point over here at the same time, because they are of the same length, and at that point they are going to be equal to each other. So this is what I'm trying to say. We place a pointer at the combined, this one is combined A combined with B. So this A combined with B, why this is B combined with A. So, and now when we place the pointer at the beginning of both of them, we keep transversing in the same proportion. You see here 2 move by 1, it's moved by 1 to this point, this one to move by 1 to this point, and then it keeps traversing. And then what we just have to do is that at each point we are going to compare the node if they are the same. So the node at this place is not equal to the number at this place because it is not shared. They are different node objects, they are different list node objects. So then we come here again and we compare the node at these 2 points. They are not the same. Then we keep going on and on, but at this point, because they both share the same tail node and they have the same length, at this point they will be the same, and we just have to return A in that situation. But there are some situations whereby the list link, both of the list link, the first and the second one, does not intersect. Don't forget, the question asks us to return null if it does not intersect. So there is probability that it will not intersect, and in a situation like that, we are still doing the same thing. Fine, we are still taking A and B and B and A. We are still finding their combined linked list of A and B and B and A. And just look at this example here now. When we put the pointer there at this their combined list, we will keep moving, and because they are the same length, they are going to reach the ending at the same time. Meanwhile, throughout they will not intersect. Why? Because they do not share the same any node together, and therefore they will get to null, and we are going to return null just as the question asks us to return. Now you might be wondering, how do we combine two linked lists A and B, and how do we form also B and A? So we don't really need to connect the ending of A with the next property or the next attribute of A. We don't need to connect it to the head of B, and we don't need to create a new instance of a linked list that is as long as node A and node B. All we just have to do is transverse node A normally like we used to transverse, and then after traversing and getting to the end, how we will know that we have gotten to the end is that the next attribute of the last node, which is the end node, will always be none, because there's no node again. So at that point we know that we are the end node, and then we just start from the head of the B like that. And same thing, if we want to do B to A, we just iterate B, and when we get to the end of B, we are going to start from the head of A. So this is the Leetcode implementation for how we can transverse from the head of A, and when we get to the last, we can continue with B without having to join them or create a new data structure. So it's just that we keep iterating, setting PTR of A, which means the pointer is originally going to be at this first node, and then we are going to tap into it next, and then we are going to keep tapping into it next, and while loop is going to keep iterating through. And when it gets to the last node here is the node whereby the PTR, when the PTR of A gets to the last node, the next attribute will be none. So at that point it will just assign PTR of A to be equals to the head node of the other one. So you see, once you get to the last, whereby the next attribute is none, it is going to perform this else statement and attach head of A to PTR of A. So that way we have access to the head of the head of the second linked list, and then we can traverse. Similarly, the same thing apply to B. We start from B and we keep traversing, and when B get to the last node whereby the next attribute is none, it's going to attach it to A. So that's simply what we are doing there. So let's quickly summarize the logic. The logic is to place two pointers, one at the head of the first list linked, the other at the head of the second linked list, and then we are going to transverse both of them in the same proportion and try to compare the node at each pointer if they are equal. So if they are equal to each other, that is, it is a shared node between the two linked lists. If they are not equal, we transverse on to the next linked list, and then once we get to the end of the first linked list, we are going to continue with the head of the second linked list, and when we get to the end of the second linked list for the other pointer, we're going to continue with the head of the first linked list so that we can achieve the same length. Now let's begin with the code implementation. We're going to be creating a class for our list node. For each node we'll be using, and the class is, we have two important attributes. So we have the value and the next attribute, so we should be none by default because of the last node. So and self dot, let's assign it initialize So we have the list now. Fine. Now let's try to create the list node and the list link structure that we'll be needing. From the diagram here, we can see that the first linked list is node 1, node 3, node 4, and the rest, which is node 8, node 7, and node 2, is shared by both the first linked list and the second linked list. So what we're going to do is that we're going to create the first linked list from node 1 to node 4. So we're going to create node 1, node 2, and node 4. I'm going to relate them to each other to form the first linked list. We are going to create the second linked list as well as node 6 and node 4. So we're not going to connect, we are going to create this linked list, node 8, node 7, node 2, and we're going to connect node 1, the first linked list to it and the second linked list to it. So we are going to see how we're going to do that. Now let's create node 1 for the first linked list. Node 1 will be a list node of 1. So similarly, we are going to create node 3. Don't forget that node 1 is connected to the node 3 in the first linked list. So node 3, we are going to create node 4, which is the third node in the first linked list. So fine, we have created a portion of the first linked list. Now let's create the portion of the second linked list that is not shared. Don't forget that this 3 portion of the first linked list is not shared by the second linked list. So we're going to be creating a portion of the second linked list that is not shared by the first linked list, and that will be node 6. So that is the head node of the second linked list, and node 4. So this node 4 will be but we don't want the name to correlate. Don't forget that these are variable names and it's gonna get reassigned to this new node, so we have to give it another name so that they won't be. So let's call it node 4_1. So fine, we have node 8 now. Node 8, this is the shared node between both of them, so we're gonna call it node 8, list node of 8. So I'm trying to explain how to draw, because if you are dealing with linked lists, we are dealing with trees, graph, tries, and other things like that, you really need to know how to convert a structure, a diagram of relationship, how to convert it into code. So now we have node 8. If you look into the diagram at the right bottom, you see that node 8 is connected to node, let's see, it's connected to node 7 and then node 2. So node 7 and node 2. Meanwhile, the node 8 is what is shared, is where the sharing begins. You understand? So now fine, we have added all of this thing. Now let's put this node 1 dot next is equals to node 2, and then node 3 is node 3. You understand? So because node 1 is connected to node 3, node 3 dot next next equals to node 4, and after that, so we see that node 4 dot next is equals to node 8. Fine. The same thing apply here. Node 6 dot for the second linked list next is equals to node 4_1, which is the other 4. Fine. Node 4_1 dot next is equals to node 8. But node 8 have not been defined at this point, at both points, so it's okay to move it downwards to where we are defined node 8. So it's okay to move it, nothing wrong with moving it downward there. I'm just putting it there to make it more explainable. So fine, you see that this way we have explained how we have converted the diagram into code. We create node 1, node 3, and node 4, and we link node 1 to node 3, node 3 to node 4, and we link node 4 also to node 8, and the same thing apply. We create node 6 and node 4, and what we do is that we link node 6 to node 4, and this node 4, which is given by the variable node 4 underscore 1, we attach it to node 8. You see that both node 8 now is shared, the same object node 8 is shared between the node 4 of the first linked list and the node 4 underscore 1, which is still node 4 of the second linked list. So that's it, how we work this thing out. Fine, let's define our the class, which is the linked list intersection class. So the linked list intersection will be taking in the first head, let's call it head A, and the second head B. So both head are actually list node, they are object of list node, don't forget list node, because they are head node of the two linked lists. So, and then the return will be, we have to return a node as well. So it's a list node, the node at which they intersect. We can now call this function here as print this, and then you can pass in add node 1 and node 6, because node 1 is the head of the first node, is the one that links to node 3, to node 4, and to node 8. You understand, in the diagram that we have in the problem statement. And similarly, node 6 is the one that links to node 4, which eventually leads to node 8. So these are the two linked lists, and these are how you can create two linked lists. So now we pass node 1 and node 6 as the head node of the two linked lists. So now, according to the logic that I want to apply, we are going to define two pointers. Let's call it ptr A, that is pointer for A, and ptr B, pointer for linked list B, and they are going to be situated at the head node for A and head node for B respectively. So, and what we want to do is that we want to keep on moving each of them forward at the same proportion until they become the same, until they reference the same node. So while ptrb, while it is not equals to ptra, so what this actually means is that let me put A and B. Sorry, supposed to be let's make it ptr. So pointer, I mean pointer, I just short it to ptr. So while ptra is not equals to, so it keep doing this as much as ptra is not equals to ptrb, mean that they are not pointing at the same head, they're not pointing at the same node, then move on to the next node. That's what we are trying to mean here. So what we do is that we pick ptra and we set it to ptr a.next. So don't forget, ptra is initially pointing at the head node, and ptrb is initially pointing at the head node also, but for the first link and the second link respectively. So if these two nodes are not equal, shift ptra to the next node. So meanwhile, that is if ptra, you understand, .next, that is if the pointer a .next attribute exists, else we are going to be shifting to head B. So that is what I mean by combined linked list of A and B. So it's going to start from the first node in the first linked list, and it's going to keep changing to the next, moving to the next and assigning it to as the new ptra. So but in a situation whereby the next attribute is 0, if it does not exist, that's what this means, that if ptra.next. So in a situation whereby ptra.next becomes none, it's gonna switch to head B, because anytime ptra, that is the pointer, is pointing at the last node, then the next node to the last node is gonna be none, and because of that it should shift on to the head B. Same thing apply for ptrb. So we are going to set it to ptrb.next. So that is if ptrb.next exists. But in the situation whereby ptrb.next is pointing to none, definitely it has gotten to the last node, and then the next node to the last node is none. So we should switch to the head A, and where head A signifies the head of the first pointer, so it can traverse the two pointers. So that way they will be of the same length, and we can now return ptra. So because it's either ptra becomes ptrb before it exits this loop. So for it to exit this loop, ptra will be equal to ptrb, or else this loop will continue to iterate. So, and definitely if ptra equals to ptrb by the time it exits this loop, we can therefore conclude that we found the node between them. So otherwise it will return none. That is when ptra get to the end of the linked list, and ptrb also get to the end of the linked list. So at that point, both of them will arrive at null at the same time, just like we explained in the logic. So if you don't understand this, kindly go back to the logic that we explained. This is just the code implementation of the same logic. So when after running the code, we have this particular object returned, but this is just a list node object to return the value, so that because the value is more presentable. So rather than this main list that is returning, so whatsoever is returned from the linked list intersection, we are gonna find the value attribute so that it will give us a number. So at this point we see that 8 is returned. So this 8, meaning that 8 is the point of intersection. And if we go back to our code here, we will see that 8 is really the point of intersection, as we can see here. So that's it. That's the solution to the linked list intersection. Thank you.